CEO of ITM Power, a company up in Sheffield. They are highly focused on hydrogen and how hydrogen fits into the economy, and fuel cells in particular. Just so you know, we're running a study tour to their factory. We're doing a morning of learning and an afternoon site visit to their factory later this month for anybody who's interested, and there are flyers around the event on those tours, so it's a little plug for that. So Graham is going to talk to us today about all sorts of energy storage technologies and how hydrogen fits into that. So Graham is the currently CEO of ITM Power. Before that he was with National Power. Before that he was involved with the Central Electrical Research Labs, and he was involved as well with a project called Regenesis, which is the UK's largest energy store, which is 100 megawatt hours. That's at Little Barford. So I think this will be a very interesting session, so I shall hand you over to Graham.
Okay, thanks very much, and thanks for that introduction. So what I'm going to talk to you about is energy storage technologies. I'm going to work through the energy storage applications and the technologies that are available and how the market's segmented. So I'll start with the principles of energy storage, say something about those applications and technologies, and then to talk about the two major subsections of energy storage. That's mechanical energy storage and electrochemical energy storage. And then talk about sector export, something that I think is poorly understood today and is a solution for renewable power intermittency. And then say a few words at the end about a business case for energy storage, and how you can look at understanding the value of energy storage in the network. So first thing to say is that the world has a huge problem. It has to decarbonise energy, and energy is actually the largest market in the world. So if you dialectically, actually that problem is a huge opportunity for the UK. And I always start by emphasising that what we ought to be doing is thinking of ourselves as suppliers of equipment for this market rather than just consumers of that equipment, because it can have a massive effect on the UK economy. One of the missing links is energy storage. If you want to electrify transport, you want to decarbonise electricity, electrify transport and electrify heat, you need some energy storage, particularly with intermittent renewable power on the network. And it's been a conundrum that people in the power sector have tried to solve for a very long period of time. Here's the problem. If you take a classical power network, generation and demand or customers are dynamically coupled together. So in any conventional power network, on the demand side, when you turn on appliances like cookers and kettles and all those good things, the network has to respond sub-second, and it does that by turning on and off generation. Okay, and that dynamic coupling has been a very important principle in the power sector, and it is sub-second, and in some cases it's down to a cycle, which is a 50th of a second. Dynamic coupling all over the world has now been undermined. It's undermined because of a very positive development, which is to decarbonise the network, we're using renewable power. The problem with renewable power, take wind for instance, is it's the wind that decides when the power generation is turned on and off. And if you give that wind priority of dispatch, then you lose control of some of the supply-demand balancing. Okay, so now we can only control, in Germany for instance, or Denmark, 80% of the power stations and when they come on and off, because it's the wind and the sun that controls the rest. So what do we do about that? Well, there's a number of things you can do. First of all, you can implement energy storage. So the first thing that's worth saying is that energy storage is additive. It's the same argument as embedded generation. A lot of small ones add up to one large one. So there are lots of places you can put it on the network. It doesn't have to be very large energy storage at the generation end. You can go all the way down to the transmission and the end of the distribution line and implement energy storage, and it's still additive. And in fact, most of the peaks on the network, the peakiest part of the network is right down at the distribution end. You can also implement demand-side management. So what you're doing then is shifting some of the control from the supply side to the demand side. In other words, you can turn on and off loads. And to do that, the best way of doing it is to control it from the power companies and from the network. You can also implement sector export, which is very similar to demand-side management, and it's very similar to what is referred to as demand reserve. You can have large pieces of plant all over the country that are ready to be turned on and off whenever you want. So if you have incoming intermittent power that you have to turn down, you simply turn on the load. And in our case, that load is an electrolyser, and we make hydrogen. We can put the hydrogen into the gas grid, or we can use it as a fuel. Well, what you do then is capture all of the intermittent renewables by having a load that you can turn on. Okay, so let me talk about energy storage. Some of the applications, technologies, but particularly the segmentation of energy storage. So I'd like to start with a very famous map. Actually, this map comes from Sandia Labs in the mid-1980s. And it segments energy storage by power size and time. That's the way you analyse what energy storage you need. And what it does, what they did is map on that the various applications for energy storage. So there's power quality, transmission, commodity energy storage, and so on. What you should notice is that right in the middle is renewable energy management, and actually it's a massive sector. It spans the full time range and the full energy range. So renewable power is intermittent at the level of seconds or sub-seconds. If you plug in a solar panel, you go from 100% current to 0% and back to 100% again, particularly in the UK, every second. It's called the cloud effect. Or you can have intermittency of wind turbines that goes all the way out to being seasonal. Okay, so we have the widest range of energy storage times required and the largest range of power. So it's the most difficult conundrum of all. So here's the technologies that you would use on the same scale. Okay, you do not use the same technology for bulk, seasonal or daily energy storage that you use for transmission, voltage stabilisation, VAR flow work, frequency work. They're different technologies. And what you do is, they've done is map those technologies onto the same axis. And actually, if you want very rapid response energy storage for networks, you are looking at technologies that have been developed for very long periods of time. If you're looking at very long, very large energy storage, trying to replace pumped hydro, then I would suggest the only technology that can do that is hydrogen. And I'll explain why as we go on. So let's start with mechanical energy storage, which is frankly the most familiar to most engineers working in the power sector. We're talking about pumped hydro, compressed air and flywheel energy storage. So let's talk about the network today. Actually, the main energy storage on the network today is inertia. So what happens is, if the network has a shock, so a lot of demand comes on, the first thing that happens is all the machines that are rotating at 3,000 RPM slow down. So 3,000 RPM is 50 hertz, which defines the frequency in our network. And they can all slow down to 48 hertz, which is 4%. That's the rule that National Grid have. They're allowed to go down to 48, up to 52, which is 4% either side, with an average of 50 hertz every hour. Okay, so what happens? We get a shock on the network, all the big rotating machines slow down because they're overloaded, then another rotating machine somewhere in the UK kicks in and they all speed up. And in fact, some of them go above 50 hertz to 52 hertz, which gives you your average. So that's the inertia in the network. It's very worrying taking off all the big steam chests, because you can't do this with gas and you can't do it with wind. And what we have to remember is that the network still needs some inertia. Okay, that's where we are today. That's called power frequency shedding. One of the technologies that was developed by the CEGB was pump storage, which does have at the heart of it a rotating machine. What you do is you pump water up into a lake, and then at a later time you let it flow down and it works as hydro. The most famous in the UK is the Norwich, and that went online in 1984. Actually, the CEGB consented for 8 sites. We built 2 of them, and the largest was the Norwich, and it cost $310 million. And that gives you a dollars per kilowatt and the dollars per kilowatt hour number. Now, very interestingly, the plant was sold to Mission Energy during privatisation at £550 per kilowatt, and that has defined in the city what they believe the value of energy storage is in the network. Actually, the EPRI long-run targets have always been $1,000 a kilowatt, $100 a kilowatt hour. And you'll note there's a different price target for the power rating and the energy rating, which is absolutely right. The important thing about pump storage is it separates power from energy. So the power rating is the turbine, and the length of time you can deliver that power, i.e. the energy rating, is the size of the lakes. And that's the case with hydrogen, and it's the case with flow cells. And it's that separation of power from energy that you need with renewable power to get the cost structure that's required. Okay, when you think about the market for energy storage, you have to remove pumped hydro. And the reason is that today, pumped hydro is massively dominating the market. All the emerging technologies are actually only emerging. They're growing more rapidly, but today there's still a small subsection of where we are. And all over the world now, countries are reanalyzing the way that you use energy storage in the network. So if you take out pumped storage, this is what it looks like. There are 2 dominating technologies: sodium sulfur batteries in the electrochemical area and compressed air energy storage in the mechanical area. Actually, sodium sulfur, unfortunately, is on hold. And one of the reasons for that is that there was a significant fire in Japan with sodium sulfur batteries, which work at around 400 degrees C. Okay, the first important mechanical energy storage is compressed air energy storage. Often misunderstood, because people think it's storing energy in compressed air and then bringing it back again. What you actually do is run that compressed air through a turbine. And what you're doing is reducing the fuel consumption in a combined cycle gas turbine plant. Okay, so it's not directly mechanical energy in and out with the compressed air. It's actually running it through a turbine. Works very, very well. Has been studied extensively in the US. The Alabama plant is a very important plant, incredibly well studied and funded by EPRI, and gives you a 25% reduction in fuel. What people are looking at doing now is putting that mechanical energy storage inside wind turbines. So rather than having it external, you do the compressed air energy storage inside a wind turbine, and then it gives you a power generation which is more schedulable. But the storage times aren't long storage times. The most famous development is the flywheel development. This is for very, very short energy storage times. It's for response on the network. Actually, interestingly, most of the technology was developed in the UK. It came out of BNFL and their centrifuges for separating radioactive isotopes. A company called Pirouette was spun out of BNFL that was then called Urenco, and Urenco, when it went into administration, was bought by Beacon Energy. Beacon Energy itself a year ago went into administration and has just been pulled out of administration again. And that very difficult set of financial stories tells you the history of energy storage. Actually, energy storage and the technologies have been available for a long time, but the mass need hasn't been there until now. And just so you understand that you can actually scale up a flywheel energy storage, here's the 20 megawatt Beacon Energy plant in the US. So each one of those little circles that you see by the buildings is a hole in the ground, and in each of those holes in the grounds there's a flywheel spinning at 3,000 RPM, or actually above. They go up well above 3,000 to maybe 6,000 RPM, so that when the inertia is taken out of them, they're always above 3,000 RPM. So they do respond in less than a 50th of a cycle. So they genuinely balance a frequency in the network. Okay, let's talk about electrochemical energy storage. Electrochemical energy storage is very significant for one extremely important reason, and that is that it's scalable. It's modular and it's scalable, and you can buy it, you can build it up on site as a very small footprint, very high energy density. We're talking here about supercapacitors, batteries, fuel cells and hydrogen. So the first thing to say is that, again, you use these in different ways. Here's a Ragon plot. And a Ragon plot looks at power density versus energy density. And all that's saying is that if you want energy storage for a very short period of time, you use a supercapacitor. A middling period of time, a couple of hours, you'd use a battery. When you get above a few hours, it's hydrogen and fuel cells that you use, because you're storing the fuel externally rather than in the battery itself. Of course, the best systems are ones that hybridize all three together. So the early work with lead-acid batteries. Whenever anyone thinks of energy storage, the first thing they think of is batteries, and in fact lead-acid batteries. So here's the problem with batteries and why they're not everywhere. When you store energy in a battery, you store it between the plates of the battery. You store it in the electrolytes. Okay? The problem then is if you want more energy storage time, you have to buy more and more batteries. That means that the capital cost goes up almost linearly with time. Okay, so most batteries are 2-hour batteries. So if you want to store electricity for 2 hours, use a battery. Maybe 4 hours, you buy 2 lots of batteries. You get above 4 hours. In fact, all of the fuel cell companies worldwide quote for energy storage schemes from 4 hours on. And if it's below 4 hours, they say, go and buy a battery. Okay? Here is Chino, which is between LA and Palm Springs. That was the big experiment done by EPRI all the way through the 80s and 90s. What you see there is banks of lead-acid batteries. And all they did is just buy more and more batteries as they wanted to increase the energy storage time. You overload a battery, and the place where you mustn't overload a battery is in discharge. And if you discharge a battery, it dies very quickly. So what you need to do is go from 100% charge to 80% charge and back again. That's why these batteries are 2 hours, not 6 hours. And if you do that, they last a very long time. Sodium sulfur was an excellent development. You can have a 6 megawatt size battery, 2 megawatt size battery. Problem is they're high temperature. Actually, they're molten materials inside the battery, and for that reason, one of them set on fire recently, and the market has wobbled for sodium sulfur batteries. It will come back, and sodium sulfur is actually an extremely good technology if you want 2 hours of energy storage. Another interesting development for batteries is A123. Their whole proposition is taking spent lithium-ion batteries from electric vehicles and packaging them up. So literally, it's like cassettes in a cassette rack, and you have hundreds and hundreds of these very small batteries racked up inside a large ISO container. And the plant at Chile is 12 megawatts. That's a power rating, 12 megawatts. Actually, it's about a 2-hour battery, and so you're looking at 24 megawatt hours. The largest plant that they've done then is a 100 megawatt plant, just under 100 megawatts. Sorry, it's a 100 megawatt wind farm and has 64 megawatt hour energy store. But as you can see, you just need to rack up more and more batteries. It doesn't separate the power from the energy. Okay, so here's a solution for separating power from energy. It's called a flow cell. And there are a number of electrochemical couples. The Regenesis one with polysulfide polybromide. There's the vanadium one, and also zinc bromide. So the principle is this, that you have at the middle, you have a reactor. You have electrochemical cells. And what they do is charge up the electrolyte. The difference with a battery is that you remove the electrolyte, you put it into a tank. Okay, so if you want to store the power for longer periods of time, you just make the tanks bigger. You don't buy the expensive bit at the middle, which is the reactor. Actually, we scaled the reactors up to 250 kilowatts. You can see the reactor there that went into Little Barford. A fantastic design, had integral seals, had composite end plates so that it could yaw. To get over thermal expansion of the tie rods there, the carbon fibre tie rods. So it was a really extremely good solution for flow cells. This is Little Barford, the plant. It's a 10 megawatt, 10-hour energy store. You can see the storage tanks and the cell hall, and there in the cell hall you can see the 10 megawatts of electrochemical reactors. So Regenesis was bought by RWE when they bought Energy, which was the leftover part of National Power. In fact, we sold one of these plants. We sold a 10 megawatt, 10-hour energy store to Tennessee Valley Authority, who were very progressive at that time in energy storage. The other couple is vanadium. So this was invented by Maria Scalasalis at the University of New South Wales, and it's the same as the Regenesis plant, but the electrochemical couple is vanadium on both sides. And the whole principle of finding a couple is that you can put a lot of charge into the electrolyte, but it still stays in solution. So all the reactants and all the products have to be in solution, so they can be pumped out of the reactor and stored in an external tank. That gives you your very low cost of pounds per kilowatt hour. So there's the largest vanadium plant that was built. This is it was built in Japan, and you can see the reactors in a very similar way to the Regenesis reactors. Finally then, zinc bromine. Zinc bromine actually is a pseudo flow cell. Only 1/2 of the reactants and products can you remove. One of the problems with zinc bromine is that every discharge cycle you replate the zinc against the zinc electrode. So it's halfway between a flow cell and a normal battery. But it's still a very interesting technology. So what's the other way of separating power from energy? Well, it's hydrogen. If you take water and power and electrolyse it, you make hydrogen and oxygen, which you store in a hydrogen tank and an oxygen tank. If you want to store that power from that electrolyser for longer periods of time, you just make the tanks bigger. So the pounds per kilowatt hour cost is very much lower than batteries if you want to store for long periods of time. And of course then you just put those reactants and products straight back through a fuel cell, which is the highest efficiency generator that exists, and you get back the power. Okay, so let's talk about hydrogen energy storage and the way that that's being implemented now worldwide. So our interest in hydrogen is, as I referred to before, as sector export. So what you're doing, and it's a particular solution for renewable power, is you just export. You're not taking the power and bringing it back into the network at a later time. You export it either to the gas industry, in which case you're responding to the Renewable Heat Initiative, or you export it as a fuel and you burn it in fuel cell cars, responding to the need to decarbonise the transport sector. This is equipment that we produce. You can see on the bottom left-hand side the electrochemical device, that's the electrolyser. That will respond in 1 second, and we can get 1 megawatt of electrolyser into a single 20-foot ISO container. So you see 4 ISO containers there. The blue ones are storing the hydrogen. So if you want to store that power for 1 day, you buy one of those. If you want to store it for 2 days, 3 days, 4 days, you just buy more tanks. You don't keep buying the more expensive. Of course, the largest tank that we have in the UK for hydrogen is called the gas grid. And actually hydrogen is completely miscible with natural gas. So our first major scheme is Eco Island. So this is the Isle of Wight, planting up with renewable power, and their desire is to become self-sufficient in energy and then become a net energy exporter to the mainland. It's being viewed by the UK government as an experiment of how you balance all of the renewable power technologies and energy storage devices together. And it's what they call a green print. And it was launched in Parliament about 6 months ago and has attracted a lot of interest worldwide, and particularly from the Treasury. So the first project's 2.4 million from the TSB. So it's a hydrogen energy storage smart grid project where the hydrogen is used as a transport fuel. We work with SSE. They actually not only are supplying the renewables, but are also buying some vehicles to use on the island. Toshiba are doing the smart grid controls. IBM, the user interface and the intelligence, and Cable and Wireless, the data cloud. So that all the vehicles on the island know where the refuelling units are and whether they're full or not. We have vehicles from Toshiba and also fuel cell vehicles from Hyundai. We're doing marine vehicles, commercial vehicles, and fuel cell passenger vehicles. So an interesting development. The Perfect Energy Storage Scheme combines a number of the technologies together. So if you want to store power for short periods of time, use a battery. And there will be a battery on Eco Island. For doing the transients work, for about 2 hours. If you want 2 days of energy storage, you need hydrogen. And that we store and we use for vehicles as a transport scheme. And if you still have an excess of renewable power that you need to store, like in the winter, you put it straight into the gas grid. The gas grid on the Isle of Wight is owned by Scotia Gas Networks. So we can inject it directly into the grid. Let me tell you a bit more about power to gas. It's my final section in this talk. So injecting gas into the gas grid, you can simplify the whole concept by saying this. If you take the gas grid on the right and the power grid on the left, the gas grid in the UK on average carries 3 times as much energy as the electricity grid does. In the winter actually it's 5 times as much. Okay, if you want renewable heat, that's the bit you've got to decarbonise. And if we think we can do it by electrifying it, well, I think we've got another thing coming. There is a transducer between the gas grid and the electricity grid. Okay, it's called power generation. But there isn't one at present going the other way, which is now the one that we need. Because often we make an excess of power in the power network and need to put it somewhere. So we can put it in the gas grid, decarbonise the gas grid and allow more renewables onto the network. You can do it in 2 ways. You can put it straight into the gas grid. All you need to do with hydrogen is match the Wobbe number, which is the calorific value divided by root density. Okay, so it's how rapidly it mixes, Graham's law of diffusion, times its calorific value. And that matches the gases going in. And they do it all over Germany now. Or you can methanate it. You take carbon dioxide and react it with hydrogen and you get methane. Actually, it's the exact reverse of the water-gas shift reaction. And that reaction then means that you are putting methane into the methane grid. So no matching required and much less compliance work required. Here's the schemes in Germany already. There are about 8 power-to-gas schemes in Germany, but there are many more hydrogen schemes for transport than there are in the UK. Although with UK H2 Mobility, which started at the end of last year, actually now we're planting up with a serious amount of hydrogen refuelling stations in the UK. The other map shows you the gas storage in Germany. One thing to understand about the German energy network is they've got much more gas storage than we have in the UK. So we were delighted to get the project from the Technology Strategy Board to look at power to gas in the UK. We work with Gas Tech at Cree, who are the compliance body working in injecting various types of new gas into the gas network. We work with SSE, National Grid and Shell to look at how that's best implemented and what changes, if any, to the legislation required. So in the UK today, you can put 0.1% hydrogen into the gas grid and you're still compliant. Actually, a very significant study was done by a gentleman called Dutton at British Gas and showed that you can put between 5 and 15% into the UK network without requiring any change to burners. And the thing is with hydrogen, if you match the Wobbe number, you still have a different flame velocity. And that's the reason everyone went round and changed those burners in people's houses in the late 70s and early 80s as we moved from town gas to natural gas. Of course, town gas was 60% hydrogen, so we've already been there with our own network. Here's an energy map. Actually, this is something that fundamentally everyone at DEC should look at. There's 3 times as much energy in the gas network as there is in the electricity network, and twice as much energy goes into road transport. The principle of hydrogen is that you can mediate between all 3. And that triangle is the thing that everybody now in Germany is looking at. So you go back from the electricity grid to the gas grid, with direct gas hydrogen injection, and you go from the electricity grid to transport with electrolyzers to make on-site hydrogen for fuel. Okay, then just finally one slide on methanation. There's what people often say is, well, what does the energy balance look like of methanation? If you take wind power and you connect it to electrolysis, you get about 75% efficiency. Actually, most electrolyzers won't couple. That's the unique thing about ITM electrolyzers, is the ability to couple directly to intermittent renewable power and take those shocks in power difference. The waste heat that you get, by the way, is low-grade heat. It's difficult to utilise unless you're in a domestic environment, because it's around 60 degrees. Hydrogen reacted with CO2 is called methanation. Okay, you need a microchannel reactor, and you react it with catalysts that are reverse water gas shift reactors. So they work at around 300, so you do have high-grade heat that you can recover. And then you go around the full energy balance. Power to power, you get 36%, which is low. But actually, you've done all of the work that's needed for the network by doing the sector export right at the beginning. So what it is 36% of something that you would have turned down completely. And in fact, if you implement CHP with it, you get up to 60% energy efficiency. Okay, I just wanted to finish with some remarks about business cases for energy storage. One of the difficulties with energy storage is once you've bought some energy storage, there are quite a lot of things that you can do with it. And if you imagine very large amounts of energy storage, you're talking about a day-night arbitrage, you're talking about frequency and voltage stabilization, black start, all kinds of things, and it's very difficult to bundle those into a single value. And one of the conundrums with energy storage is how do we value it? I would say the best report I've seen so far, I think hydrogen, by the way, in this report was completely misunderstood, and their Boston Consulting Group need to go to Germany to see the massive number of schemes that are now going on. But for all the other energy storage technologies, it's a good analysis. What it tells you is all the jobs you can do with energy storage and how to value them. And a very worthwhile report to look, and it's free online. So some predictions then. What they say, and I would totally agree, is that there comes a threshold with intermittent renewable power. It's about 8% by energy and about 20% by capacity. And then you start to have to turn down very significant amounts of it. And the market for energy storage will track the deployment of renewable power, which I would completely agree with. We're talking about internal rates of return of around 30% and up. And we're talking about markets, many markets, of the 50 billion size. So actually, as we plant up with renewable power, there's becoming a realization that if you use a new sort of power generator, you need to manage the grid in a new sort of way. And that means doing some export and also some energy storage. So let me get right back to the first slide. This is a fantastic opportunity. Their markets are massive, the rates of return are very high. My interest is in making sure that in the UK we make some of this equipment, we manufacture it here, and we get some benefit to the UK economy, rather than just being users. And in fact, most of the technologies that I've talked about today were invented in the UK. We just didn't follow the journey for long enough. So thanks very much. And are there any questions? Yeah. So a microphone for the gentleman here. Do you want to hold on till the microphone comes and I can hear you?
Thank you very much.
Oh,
Tony
good.
Day,
That's great. Hello, Tony.
consultant. I'm leading a group who are looking to resurrect the British gas methanation technology.
Okay, great.
So we actually got the other half at the bottom of one of your diagrams.
Yeah.
British gas, the HICOM, which is combined shift and methanation, is the world's most efficient methanation technology, and it's just dying to get into bed with some of your hydrogen.
Yeah, that's fantastic. I mean, the reactors that we make are on-site hydrogen generators, so I think match perfectly with what was had at British Gas. Well, I mean, I'm delighted that they decided to resurrect that, because the markets are growing very, very quickly.
In China, under the current 210 to 215 5-year plan, there is sufficient SNG, synthetic natural gas, capacity being built to supply the whole of UK gas demand. And a similar scale of development was done in USA in the early 70s, where the British gas, high-speed gas, naphtha to SNG process was developed in the States. Again, in 5 years, they built enough SNG capacity to supply the whole British gas grid. So that technology at that size exists and is well proven. As you said, we got it.
Yeah, I mean, so many times you look at innovative energy technologies, and we invented them, we patented them, we published them, then we walked away from them, and then 10 years later you see major economies around the world adopting them, and it's a terrible shame. We shouldn't do that with methanation. Just to say, the Regenesis technology, by the way, is owned by a Chinese company now, and so is the vanadium technology.
The possibilities of methanation and of making liquid fuels, liquid motor fuels from hydrogen, really makes much of the hydrogen economy redundant, doesn't it? We want hydrogen, but we want a few molecules of it in between the electrolyzer and the conversion plant.
Yeah, okay, so let me tell you, in terms of vehicles, the best fuel for a vehicle is pure hydrogen. And the reason is that you put it into a fuel cell, which is 60% efficient, not into an internal combustion, which is 30% efficient. So you get twice the efficiency if you use pure hydrogen. But if you want renewable heat, and you're looking at the Gibbs free energy calculations, then it's an entirely different story. And you can make methanol and you can make methane and put them directly into the gas grid, and you've got no storage issues or transport issues. So I would agree with you, liquid fuels are fantastic. We need to be looking at gasification of coal, Fischer-Tropsch fuels, all those things that we were so brilliant at in the UK over half a century.
As long as you're talking about using hydrogen directly, you're locked into the major energy losses of liquefying or compressing hydrogen.
Yeah, the losses aren't very much for compression. I agree with you about if you liquefy hydrogen and transport it, it does boil off, and you can't screw the top on, as it were, because it overpressurizes. You have to make it on site, so that you don't have to liquefy it or transport it. We make it on site, and you actually drive up to the electrolyzer and refuel. So there's no energy loss in transportation. We make hydrogen for 56 kilowatt hours per kilogram, and we spend 4 kilowatt hours taking it from ambient pressure to 700 bar, which is where you use it as a fuel. So actually the energy requirement for the compression is very little. The energy requirement for transportation is high. That's why we make it on site. But we make it with renewable power. So you use the electrolyzers to balance against renewable power, which means it's zero carbon footprint, because you make a space in the network for renewable power to come on. So you've got zero carbon footprint and you've got zero transportation cost of a fuel. There isn't another one. Hydrogen's the only one.
I suspect that the figure you're quoting for 1 bar to 700 bar is in fact a figure for electrolysis pressure to 700 bar, isn't it?
No, it isn't, no.
What is the electrolysis pressure?
Actually, we make electrolyzers that work at 15 bar, so they come in under the Calagas regulations. We make an aircraft refueler where the electrolyzer works at 30 bar. We make our gas inject module, which works at 80 bar, so that you can inject directly into the gas grid, the high pressure gas grid, without any need for compression or buffer storage. So actually we designed an electrolyzer specifically for the pressure of the high pressure network. Although today you'd want to put the hydrogen into the mid pressure network at 10 bar, for the obvious reason that you can control the direction in which it goes. And most of our schemes go directly to a gas turbine or a district heating boiler to decarbonise them. So you're putting wind into a district heating boiler basically.
Thank you, Graham.
Hi, Gary Sturgeon from DEC. Hi. Just really blue skies now with your most optimistic outlook. Do you see any possible future role or future scenario where we might see an all-hydrogen gas grid? It's 100% hydrogen, there's no natural gas going into it, all our appliances in the home as well run on hydrogen, or is that just wishful thinking?
No, I think you can do that. The devices need to be modified for flame speed to do that. The high density polyethylene pipe in the lower pressure network is good for hydrogen. All the welds at 80 bar seem fine as well. I mean, our whole network used to be 60% hydrogen, of course, with town gas, gasifying coal. I think it's something that is built up progressively, actually. I mean, I would say one of the interesting areas is you can utilise wind without a grid connection using hydrogen. So if you've got wind resource and you can't, it's not cost effective to have a grid connection, of course you can put the energy into the gas grid or a gas tank or a vehicle. So, you know, when I said it helps you utilise more renewable power, it's not only about supply and demand balancing, particularly at night when we run base load, it's also about being able to build remote farms.
Yeah, I think that was the question, whether we could actually create enough hydrogen to run an entire gas grid. Maybe in renewable form, not by using fuels as fossil fuels as the basis.
Sure. I mean, just to explore that a bit more, you know, with renewable power, what you do is you buy a capital asset, and then when you've amortised that, your electricity is free, because you don't pay for the wind or the sun. That's the win on a national level. It's all about energy security, and the same is true of an electrolyser. If you put down a piece of renewable and an electrolyser, you're not buying gas or fuel anymore, because you utilise the wind. It makes the power, you put it through an electrolyser and you make the fuel. So it's the same proposition as renewable power in terms of balance of payments and in terms of fuel and energy security.
I'd like to respond to a gentleman from DEC who I didn't see. Bit of history. When Britain converted from town gas to North Sea gas, in the following 40 years, the total energy flow through the gas grid multiplied by a factor of 10. That was partly due to the availability of cheap North Sea gas, but it's also because methane is a higher calorific value energy vector than hydrogen. If you wanted to convert the grid back to hydrogen, apart from all the technical problems, whatever those might be, you'd either have to greatly reduce the total energy flow or rebuild the grid, which is expensive. We think it's much cheaper economic in terms of UK PLC to react hydrogen into methane and keep the grid operating as it currently works?
It's a very good point. I would agree with that. It's about gas mixing. I think that's absolutely right. It's the calorific value that's required for generation. I mean, one of the things that the Germans are looking at now is higher pressure turbines that can be pure hydrogen. So if you look at Siemens and all of their developments, they're all about 100% hydrogen turbines. But right now you mix it without a doubt.
I hate to dispute with Tony Day because I'm only an electrical engineer, but I've been working with some German chemical engineers who are keen to bring in the hydrogen economy, and representing them. They tell me that because the gas molecule is much more agile than the methane, that the transmission in terms of kilowatts, not kilowatt hours, in terms of kilowatts is much the same. Very little change in the transmission capacity. Storage is another matter. Hydrogen would be much harder to store between seasons, for instance, than methane.
Yeah.
So there's that point. The other point that I'd like to make, and I think we should all be singing from this hymn sheet, is that the big boys in the electrical and nuclear industry are saying, we'll go for a carbon footprint of 50 grams of carbon dioxide per kilowatt hour. We should say that, well, I say the gas industry should say that, because it's actually only something like that that is really going to make the big boys with the money and the politicians wake up and realise that the gas network can be decarbonised and probably at lower cost than the electrical network. And here speaks an electrical engineer.
Good. Thank you for that. One other point I'd make about methanation and the British gas technology is that with hydrogen, renewable hydrogen, you can remove the CO2 from biogas. And so you methanate it internal to a body of methane, which actually for biogas could be a very important step in being able to bring that into the gas network.
So can I know how much mixing does the Germany with hydrogen they do, and what modifications did they have to do in introducing hydrogen into the grid?
Okay, the legislation for putting hydrogen into the grid in Germany is much less than it is here, and all over Europe it's much less. Today there are a number of pilot megawatt schemes for putting hydrogen into the gas grid, and that is a tiny fraction. It's a fraction of a percent. I mean, the energy balances that you can produce are really huge. You're talking about being able to put the whole of our winter peak of 60 gigawatts straight into the gas grid, and you've only got, in winter, you've only got 20% of the energy. So, I mean, the energy balances work in favour of the gas grid in the sense that you can spill as much as you want from the power grid, you're still only going to be a few percent. But the legislation, the consents required to do it in Germany are much less than the UK. You match the Wobby number, so it's the calorific value divided by the agility of the molecule, as that gentleman puts it.
Gaynor Hartman from the Renewable Energy Association. It was a shameless plug really. Just we're mentioning about taking biogas, taking the CO2 out, putting that in the grid. Just to say that our subsidiary, REAL, runs the Green Gas Certification Scheme, which really tracks contractually the putting in of gas in one location and taking it out somewhere else. And actually it has now been used for the first time, and green gas certificates have been now awarded. But just in case anyone hadn't heard that we did that.
Marvellous, thank you. Okay, thanks very much for listening.